What's going on, Science 10s? Mr. Walton here. What's the largest a cell could be? I'm curious because we've always talked about cells being pretty small. All bacteria are microscopic. All the cells in your body are microscopic. Why aren't you just made of one giant cell? Wouldn't that be better for you? Why are you made of trillions of cells? Let's draw two cells, one big one and one small one. Now that we know a little bit about cell transport, we know that some substances can diffuse through the membrane into the cell, or they could be actively transported into the cell. But what happens to the substances once they get into the cell? We can assume these substances might be required anywhere inside the cell. So how long would it take for these substances to diffuse into the center of the cell? Let's take a look at what I mean. When we go to draw our two cells, we're going to draw one large cell and one small cell. So here's our large cell, and here's our small cell. Now, what we want to think about is how much time will it take for the nutrients that have already diffused inside the cell or are being actively transported into the cell. So we've got some nutrients that were just either transported into the cell or they've already diffused inside the cell. And what we want to know is how much time is it going to take for these nutrients to get to the center? We're going to test how long it would take for nutrients to diffuse through the cell or to the center of the cell. This pink stuff here is gelatin with phenolphthalein in it. The phenolphthalein turns colorless in acidic conditions. So we're going to model the diffusion of nutrients in a cell by submerging the cubes of gelatin in hydrochloric acid and timing how long it will take for all of the color to disappear. We'll start by cutting the gelatin into 3 4-centimeter cubes. The first cube will remain intact with dimensions 4 centimeters by 4 centimeters by 4 centimeters. The next portion will be cut into cubes with dimensions 2 by 2 by 2, but the total volume of the cubes will remain the same as it was before. The last portion will be cut into cubes with dimensions 1 by 1 by 1, but again, we will save all of the portions, so it'll have the same total volume as a 4 by 4 by 4. We now have 3 beakers with the same total volume of gelatin inside of them. However, we cut them so that they're made of individual cubes with different sizes. We will now add 200 milliliters of hydrochloric acid to each beaker, and we will start the timer. Now we just play the waiting game. Because the smaller cubes took the least amount of time to turn colorless, we can infer that it will also take less time for the nutrients to diffuse to the center of small cells as opposed to larger cells. What is the reason behind this? Larger cells have a greater distance from the membrane to the center, but they also have a greater surface area to be able to transport nutrients into the cell. So, what's the deal? We're going to talk about the ratio of the surface area to the volume. Cells are open systems, and an open system just means matter can exit and enter. This means that a cell must transport materials into and out of itself in order to survive. The transfer of materials to and from a cell occurs through its cell membrane and supports all the cellular volume within it. If a cell becomes bigger, its volume increases. And that's not too hard to understand. If something's getting bigger, the amount of space inside of it is also getting bigger. In order to support the functions of a larger cell, more molecules will need to be imported and exported from the cell. Imported in the sense of nutrients and exported in the sense of wastes or things that the cell wants to get rid of in order to send to other cells. The distance that these molecules must travel within the cell is also going to increase. We've talked about that earlier when we drew our large and small cell. In order to support this, the cell's surface area must also increase. And I hope that makes sense. As the cell gets bigger, it's going to need more surface area because the greater the surface area, the more contact there is so that it can import or export material. However, surface area and volume do not increase at the same rate. What that means, when a cell gets bigger, one of these two things will get bigger faster. And that's what we're going to try and figure out. We're going to take the ratio of the surface area to the volume for a few different cells. The larger the surface area to volume ratio, the more efficient the cell transport will be. So let's define some things first. What we're going to do, because we used cubes in the experiment, we're going to draw a cube. So bear in mind, Mr. Walton's not amazing at drawing, but he's okay at drawing cubes. Hopefully that's universally recognizable as a cube. Now let's define some things about this. The surface area, or I'm going to abbreviate SA, the surface area is equal to the sum of all of the faces on this cube. It's all of the areas combined or added up. So what we have to think about is, well, what shape is every single face on this cube? Every single face is a square, and they're all identical. If we're saying that this is a cube, every single face here should be the exact same. And how many faces will a cube have? Well, it'll have one on the front, one on the back, one on the side, another one on the side, one on the top, and one on the bottom. So when you think of all the sides, there's going to be 6 identical faces. And what's the area of every single one of these faces? Well, it's just going to be the length times the length. So the surface area is going to be the length squared times 6, or 6L squared, whatever you like. So that's how we're going to calculate the surface area. The volume for this thing is how much space does this occupy? And the way you calculate volume for regular prisms is you take the length times the width times the height. But in this case, they're all the same. The width is the same as the length, and the height is the same as the length. So the volume for this object is just L cubed. So what we're going to do is we're going to calculate the surface area for 3 different size cubes calculate the volume for 3 different size cubes, and then we're going to take the ratios of them, and we're going to see which one has the greatest surface area to volume ratio. So we've laid out an example here of what's going on. We've got a cube with side length of 0.1 centimeters. That's 1 millimeter. So when we calculate the surface area, this is going to be the surface area of all of the surfaces on this cube. We take the length squared and multiply it by 6. So with a cube that's 0.1 centimeters, the total surface area of that cube is 0.1 squared times 6, so 0.06 centimeters squared. Sure, no problem. When we go to calculate the volume is just the length cubed. So we go 0.1 raised to the power 3, so 0.001 cubed. When we take the surface area to volume ratio, what that means is we're going to take the surface area and we're going to divide it by the volume. So we take our surface area, which was 0.6, and we divide it by the volume, which was 0.001, and we get 6,000. So this is a 6,000 to 1 ratio. Now, we're going to try this. We're going to do this calculation for 3 of these examples. I'm going to do it for the first one, and then what I want you to do is I want you to do it for the other 2. So let's go ahead and dive right in. The surface area of a 1 centimeter cube, that was the small cube. The surface area is going to be the length squared times 6. So we're going to take 1 centimeter, square it, and multiply it by 6. Well, on my calculator, 1 squared is 1, so 1 times 6 is just 6 square centimeters. So that's the surface area for a 1 centimeter cube. The volume is going to be the length cubed. So the length is 1 centimeter raised to the power 3. When I put that into my calculator, that's the same thing as going 1 times 1 times 1. So we're going to get 1 cubic centimeter. So what we're going to do is we're going to take those values and we're going to take the ratio of them. The surface area to volume ratio is going to be whatever the surface area was, 6 centimeters squared. And we're going to divide it by the volume, which was 1 centimeter cubed. And when we do that, we're going to get 6 divided by 1 is just 6. So that's a 6 to 1 ratio. So already you can see that when we increase the size, all we did was we increased this cube 10 times. That's all we did. So we had a cube that was tiny and we increased the size 10 times. So what happened to the surface area to volume ratio? Well, for the smaller one, it was 6,000 to 1. For the larger one, now it's 6 to 1. What's happening is as we increase the size of this cell or the size of this cube, our surface area to volume ratio is decreasing dramatically. So what I want you to do for the rest of this notes package, for the rest of today's lesson, is I want you to calculate the surface area to volume ratio for a 2 centimeter cube. That was kind of the medium sized cube. And the 4 centimeter cube, that was the large cube. So go ahead and calculate the surface area to volume ratio of both of these. And then I want you to answer the question, what can you say about the relationship between the surface area to volume ratio and the time it takes for nutrients to diffuse to the center of the cell? It would be best if you included the times for both of these? So we saw the times in the video earlier. Just go back and write down how much time it took for the small, the medium, and the large cubes to lose all of their color. And I want you to form some sort of a relationship between the surface area to volume ratio over here on the right and the amount of time it took for them to lose their color. The rest of the information will be in the filled out notes. You can check your answers to the filled out notes package. Have a great day and let us know if you have any questions.